Testing 1, 2, 3. All right, we have audio. So my bad, the last few video recordings didn't have any audio. So they're even less exciting because I'm just kind of writing and occasionally waving my hands around. So as far as I can tell, we got audio right now. And I ordered a clip-on wireless microphone so I can walk around away from the mic and you can still hear me, hopefully. So this is a work in progress, but we'll get there. And I appreciate any feedback from anyone, especially things like there's no audio on the recordings. That's helpful. All right, any questions up to here? We've been talking about sets and set theory, yes. 1.3, number 8b. Let me see if I can get there. Okay.
Yeah, I guess because we got this, but we run the intersection when it goes through with it, like this, and then you gotta wait around. Because if it does, it's gonna be a part of the stack set J.
All right, so section 1.8 you said?
1.3, number 8.
1.3, number 8. So we've got the sets with the circle and the square and the cross?
Yeah, the second part of the part B.
All right. So let me write this out and then we'll... So A equals circle, square, and the railroad sign. And B is a square, a sleeping cyclops, and a circle. All right, so what are the cross products? We need those first, even though we did those. So A cross B is going to be a collection of elements where each element is a tuple. First piece of the tuple comes from A, second piece comes from B, right? So it's basically all the combinations. Right, like that. And then B cross A. Same thing, but different order. Everyone agree on those cross products?
Yeah, that's what I got.
So now part B is asking about the intersection. And what did you find in the intersection?
I got 2 dots and 2 squares.
Okay, so 2 dots and 2 squares. And what?
The 2, there's a dot and a square and a square and a dot.
So a dot and a square. And a square and a dot. And I think that's it, right? So it asks you to guess a general rule for the intersection of this pair of cross products. Any guesses?
They both have to do with what A and B have in common.
They have to do with what A and B have in common. because if A has one set of symbols and B has another set of symbols, their cross products are going to be completely disjoint, right? A cross B, the first symbol in each tuple is going to be from set A. B cross A, the first symbol is going to be from set B. So if B and A don't have anything in common, none of those tuples are going to match. So there's got to be some overlap. And if there's a symbol that's in both A and B, that could be the first element of a tuple, right? Because it'll be in a tuple from A cross B, because it's the first element of A, and it'll be in a tuple for B cross A, because it's the first element in B. So it's got something to do with the intersection of A and B. Well, what is the intersection of A and B? Yeah, dot in the square.
Is equal to A, the union of A and B cross the union of A and B?
That seems like a reasonable theory to me.
I don't know if that sounds really useful.
So if we take the intersection of A and B and we cross product with itself, we should get maybe cross product of AB intersected with cross product of BA. And I think that's probably a correct rule, and I think we could probably prove it.
Bracket terms, cross product and cartesian product.
Yeah, I'm using them interchangeably. I guess because there's a cross in there.
It reminds me of the vector products. That's why I
Yeah, yeah. So yeah, I think that's probably a fair rule.
Could you do like, what was it, for 1.24, could you do A, or like, because I'm not sure I did it correctly, I wasn't sure about what you were wanting out of that.
1.24. So let me ask you a question. I've been saving snapshots of these and putting them into a PDF. Is there any value in that? Yeah? Okay, I'll keep doing that. Because I figure it's probably easier than going through the video. And let me make sure that that didn't kill my audio. Testing 1, 2, 3, we're still good. All right, so 1.2, sorry, which number?
4A.
4A. So give specific examples to show that this is true.
Yeah.
So for all of these questions in part 4, we're told what the universe is. So the universe is the integers from 1 through 9. So any sets you come up with, A, B, and C, have got to come from that universe. Don't start putting in dots or letters or things. And we want a set where A is a subset of B, B is a subset of C, and A is a subset of C. So we're not proving this, we're demonstrating that it's believable, at least in certain cases. You could be lazy and make A, B, and C the empty set, and this is certainly true, but that's not very illuminating, right? Same if you made A, B, and C the entire universe. So did you come up with an example?
Yeah, I said that like A was 1, 2, 3, and B was 1, 2, and then I said C had to be either 1, 2, or 1, 2, and they would all be true.
So careful of the order. So this is saying A is a subset of B.
Oh, yeah. So I might have gotten that backwards.
Okay.
Right, so then C, B, and A.
Okay, so C could be 1, 2, 3. B could be 1, 2, and for example, A could be 1. So A is definitely a subset of B, and B is definitely a subset of C, and in fact, A is a subset of C. So that's a good demonstration of that property. Does that make sense to everyone? Yeah.
Now that we're in 1.2, can we go over the concepts in number 6?
Number 6. Yeah. Suppose U is an infinite universal set. So the universe has an infinite number of things in it. And suppose A and B are infinite subsets. So they have an infinite number of things. So part A, the book writes A with a C on top, right? That's just the complement. That's an A bar, which is also the universe with A removed, which is also, the universe minus A. So we have 4 ways of writing complements now. So the book uses a little C on top, just put a bar on top if you like. So part A is asking the complement of A, does it have to be finite? So what's the nature of the complement of an infinite set? You're starting with an infinite universe, you're throwing away an infinite number of things. Are you left with something finite, something infinite, or can't you tell? It could still be infinite. For example, the set of all integers could be our universe. A could be the set of even numbers. The complement of A is a set of odd numbers. That's still infinite. Could the complement be finite?
Yes.
What's an example?
You take a set of positive numbers and complement with a set of all numbers greater than 2.
Sure. Okay, perfect.
You get the empty
So if you take all the positive numbers as a universe and you take the infinite set of integers bigger than 2, the complement of that has 3 elements in it, 2 elements, 1 and 2. So the complement could be finite, it could be infinite, you can't say. And that's an interesting thing about infinities. Sometimes you can pull out an infinite number of things and you're still left with an infinite pile of stuff. Alright, so part B asks about the union of 2 infinite sets. What's the nature of that? Finite, infinite, or can't tell? That's going to be infinite. Because this union is going to contain everything that's in A, and we already know A has an infinite number of things. So the union is definitely going to have an infinite number of things. So that's infinite. What about the intersection?
I think that could go both ways too.
That could also go both ways. So the set of odd numbers intersected with the set of prime numbers is infinite. Well, that's the set of odd primes. And that's infinite.
The set of odd numbers intersected with the set of even numbers, just the empty set.
Is the empty set, which is the most finite of all. Perfect. So that question is really kind of exploring the ideas of infinity and starting to acknowledge this fact that infinity is kind of weird. It does strange things. All right, other questions?
1.5, number 2.
1.5, number 2. Particular section, A, B, C, or D?
A.
All right. Let's look at part A. So calculate the following series, and it says the sum from k equals 1 to 3 of I to the n, and we're told n equals 1, 2, 3, 4. There's all kinds of ambiguities in this question.
Is that a set of n equals the set of numbers?
I believe what they want here is they want you to do 4 things. They want you to calculate the series when n equals 1, then calculate the series when n equals 2, and then 3, and then 4. So you're going to come up with 4 answers for part A.
Is I a variable or just whatever the negative?
This is the other issue with this question. I might be a typo. Maybe it should be k. Or it just might be I as I. It's just a variable. So I would take it literally the way it says and just treat I as I. it's going to be part of your answer when you're done, because we don't know what the value is, so just treat it symbolically as a symbol. So this sum, so let's start with n equals 1.
Just what, 4 sums or 1 sum?
4 sums.
Okay.
Yeah, that's my interpretation of it.
Okay.
So for n equals 1, this is the sum from k equals 1 to 3 of I to the first, which is just I. So if k equals 1, what's I equal to? I. If k equals 2, I is equal to I. If k equals 3, I is equal to I. This is just 3 times I. Similarly, sum from k equals 1 to 3 of I squared. Well, I squared doesn't change depending on the value of k, right? So this is just going to be I squared plus I squared plus I squared,
That's just gonna be 3.
which is 3 times I squared. And then 3i cubed, 3i to the 4th. But let's suppose that this is a typo. And let's suppose they really meant to ask the sum from k equals 1 to 3 of k to the n. So if n equals 1, this is k, sum from k equals 1 to 3 of k. So what is this sum equal to? If we spell it out. Yeah, set k equal to 1, this expression is equal to 1. If k is equal to 2, this expression is equal to 2. If k is equal to 3, this expression is equal to 3, and the summation says add these together. So the answer is 6. So that's for n equals 1. For n equals 2, this is the sum from k equals 1 to 3 of k squared. And this is just a shorthand for set k equal to 1, evaluate this expression, it's 1 squared. Set k equal to 2, evaluate this, it's 2 squared. Set k equal to 3, this is equal to 3 squared. Add them up. So this is 14, and so on. Yeah?
Doesn't matter which one we do.
If you see this on a test, raise your hand and ask. Okay? If there's an ambiguity, don't assume one way or another. Just go ahead and ask, because that's my bad. On a homework question, right, come to class and ask. If you don't have an opportunity to ask, pick a way that makes sense to you and put a little note. This was ambiguous, I assume it's meaning this. And then go ahead and do it. What do these summation symbols look like from programming? It's a loop, right? This is a for loop for k equals 1, k less than or equal to 3, k plus plus, sum equals sum plus k squared. Initialize your sum to 0 outside the loop. That's exactly what this is capturing. We're incrementing k each time, and each time we're calculating this new value of this expression, and we're adding them all to a running sum. Yeah?
Would B just be 20?
You're summing it 5 times. So it would be 100, yeah. Basically take the expression and add it to, you know, whatever each expression is for whatever range the index runs from and to. So we could actually define multiplication for integers. Like this. It's not a cross product anymore, that's just multiplication. One integer times another is just adding that first integer b times, where b is your second integer. We'll prove this in a few weeks. It's actually tricky to prove that this actually always works. But we'll prove that if you add n ones together, you get n for any positive integer n. It's not easy to prove. All right, good on homework?
Can we do one more example with the U in it?
With u in it.
Yeah.
You mean a
instead of
union?
Yeah, union.
Like which? There's a lot of different ways to make problems that involve. You want just union of sets, or?
Yeah.
Oh.
There's the homework problems. I think 6 or in the same exercise.
In 1.5? Which section? 1? Sorry, I'm not seeing union questions.
Or you can make up a problem. I just want to see how it's affected.
There's so many examples.
So yeah, examples. Like that. So the union's going to be everything that's in A and everything that's in B, right, all gathered together. So we can certainly start with all the elements in A, and then any element in B that we haven't already listed, right? So 2, it'll include a 3, but we already listed 3. It'll include a 4, it'll include a 5, but we already listed 5. And that's it, that's all the elements, so the union looks like that. Intersection, you need to find things that are common. So you can start with A and just go through each element, and if it's also in B, then it's in the intersection. So 1 is not in B, 3 is, 5 is in B, 7 is not. So that's your intersection.
For 1.5 number 4, do we write in a proof format or do we just solve it?
1.5 number 4, verify the following properties. It's not going to be a proof like, you know, conjunctive simplification, blah, 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 right? But what I'd like you to do, I think I put some notes in here on the assignment. What I'd like you to do is, so let's look at part A, for example. This is a really good one to ponder. So we're asked to show that the sum from I equals 1 to n of ai plus bi is equal to the sum from I equals 1 to n of ai plus the sum from I equals 1 to n of bi. So what I'd like you to do is expand this out based on what a summation means, right? Get rid of the summation symbol, write this out explicitly. Get rid of the summation symbol, write this out. Get rid of the summation symbol, write this out. And then explain why what you've got on this side is the same as this side. And you'll probably use basic properties like commutivity, associativity, things like that. And spell out the reason, right? Something more than you can just look at it and see they're the same. Okay, put something mathematical-ish in there. And then for part B, we're doing the same thing, but with multiplying inside or outside the summation. Have you seen these before? Yeah. This is how we prove these properties of integrals. If you have the integral of f plus g, that's the integral of f plus the integral of g. And the integral of f times some constant is just the constant times the integral of f. So it lets you manipulate integrals by pulling things out or combining things. That works because integrals are really just summations. They're just infinite sums, usually of very tiny things, but the principle is exactly the same. So for your homework tomorrow, try to staple your homework. Okay, there's a stapler in the collaboratorium. There should be one at the front desk. I just put staples in the one in the collaboratorium. So staple your homework. If you have frilly edges on the side, try to tear those off. The reason being not just the little pieces of paper that it leaves everywhere, but sometimes it catches other people's homework assignments, and I'm misgrading an assignment because it gets caught in the edge of someone's. And try to do your problems in order, okay? So whatever the numerical order is, section 1, section 2, and so on, in order, because sometimes I miss pieces of a problem, or I have to look around to find the problem, and try to clearly indicate, right, these, you know, chapter 1, section 1.3, question 5D, it's a lot of subsections, right? But if you can just sort of clearly write that and maybe box it or something so that I can actually tell which pieces go with which, that helps me know if you did the problems or not. All right, so you ready to talk about functions? And keep checking my sound because I'm like nervous about it. Yeah, it works. So we had this definition of a function as a mapping or an association from elements of one set to elements of another set. So we write f goes from A to B, and for each element A in the set A, f maps to an element which we can write f of B, which is contained in set B. And so one example might be a function f that goes from the set of all integers to the set of all integers. And we might define it by saying f of x is equal to x squared. So it takes an integer x and it maps it to the square of that. So f of 1 is 1, f of 5 is 25. And there's some terminology we can use. So the set A is called the domain. That's the set of things we're mapping from. The set B is called the codomain. It's the set of things we're mapping to. But here's an interesting question. Every element in A is something we can apply f to, right? F has to be defined across the entire domain. If we have a function that takes square roots, we can't say the domain is all numbers, because you can't take the square root of a negative number unless we're doing complexes. So f has to be defined everywhere in the domain. But if the codomain in this case is a set of all integers, is there always some number that maps to any given integer in this codomain for this particular function f, but probably not with integers. So if we restrict our domain to be the set of integers, 0 maps to 0, 1 maps to 1, 2 maps to 4, does anything map to 7? Right? Is there any integer whose square is 7? No. So there's a subset of the codomain which we call the image, which is the set of all functions applied to A, where A comes from the domain. So in this case, the image would be the element 0, 1, 4, 9, 16, 25, and so on. 0 maps to 0, 1 maps to 1, 2 maps to 4, -1 maps to 1, -2 maps to 4. These are the only values that are actually mapped to, and that's a subset of the codomain. And we can write this symbolically as f of the set A. And this is a shorthand for saying take every element of A, apply f to that. And this is the set of all the values you end up with. So it's f of the set containing f of every element in A, basically. And sometimes we use the word range, but it's apparently ambiguous. Usually range means the image, but sometimes it's used for the codomain. Depends what kind of math course you're taking. So I'll try to avoid using the word range. And if you see that term, it's fair to ask, what does the range mean in this case? And if you see it in the text, it should be defined. But if you just kind of see it walking down the street or something, you can say, hey, what are you? So domain is what you're mapping from. Codomain is the set that you're mapping into, but you may not map to every element in the codomain. Okay, the image is a set of all the things that you map to. So anything in the image, there's something in the domain that maps to it. Is that clear? So we can start defining properties of functions. Let me start over here. So the first notion is equality. So two functions f and g can be said to be equal if the following is true. So they have to have the same domain and codomain. And they have to have the same values for all points in set A. For every element in the domain, f and g have to map that element to the same value in B, the codomain. So it's kind of the definition you would hope for. Right? Two functions are the same if they basically come from the same things, go into the same space, and they map points to the same values everywhere. Then we say they're the same function. Are they actually the same function? That's an interesting kind of existential question. But we'll call them equal because they map to the same.
Could it be something like 1 plus x and x plus 1?
Yep. Yeah. So those will map every point to the same value. Is x plus 1 the same function as 1 plus x? I don't know. Maybe not. But they are equal.
I'm thinking like if a was all integers maybe,
Mm-hmm.
would x and x plus 1 be the same function?
No, because x would map 2 to 2, x plus 1 would map 2 to 3. So that part would be, right? So it's got to be point by point. But you're describing something we're going to talk about tomorrow or Friday, which is a one-to-one mapping between the elements of this set and the elements of that set. So we're gonna spend a whole class talking about that. So f of x equals square root x. Well, this is not a function if the domain is a set of integers, and the codomain is also the set of integers. So let's just assume we're doing f from z to z. This is not a function because it's not defined for every integer. Right? We can't find a square root of 2 that's contained in the codomain. So that's not a function. If we define f to go from the integers to the reals, that's closer to a function. We can find the square root of 2, that's a real number, but we can't find the square root of negative 2, for example. So if we do f from, say, the positives to the reals, that's a good function. Or if we do f from the reals to the complexes, that's also a function. So whether or not a function is even well defined depends very much on the domain and the codomain. Same function, but not a function here, functions here. So we always need to keep in mind the domain and the codomain. And functions can be very odd things. For example, all my functions seem to be named f. We could take a function f from z to z, and we could define it as f of n equals the rightmost digit of n. So f of 17 would be 7, f of 5,412 would be 2. Is that a function? Absolutely. It's not a cosine, sine, square root kind of function, but it's a mapping from the set of integers to the set of integers. And in that case, the image of f would be what?
Integers 0 through 9.
It would be the integers 0 through 9. Because those are the only values that f maps to. Yeah.
I have kind of a weird question
Okay.
about functions. So like, say we have a function f of n, such that, equals n plus 1, and n is an element of the natural numbers. But so like the set of natural numbers goes on infinitely, right?
Mm-hmm.
But we know it starts at 1, right?
Sure. I think so, yeah.
But the image would start at 2 but still go off into infinity. Would they both be infinite sets, even if we know that this new image is missing one value from the beginning?
They're both infinite sets.
Okay. And is the image still, are they the same cardinality then?
So the image,
we're missing that one element at the beginning.
they're both infinite. And cardinality, this is what we're talking about tomorrow, cardinality describes basically how big a set is, right? These will have the same cardinality. The reason being there's a one-to-one mapping between the elements of this and the elements of that. That's how we're going to define equality of cardinality. So for every element here, there's an element here, and vice versa. That's enough to give our sets the same cardinality. And we have a name for this cardinality. It's actually Aleph naught. I might have drawn a mirror image of that. We're going to spend tomorrow talking about that.
So if you have a function that when given one answer it could return two, I know there's a few in math, like maybe the square root of numbers, the square root of x that has an image of all, like
Could be positive or negative, right?
Yeah. Or could be like I or something.
Mhm.
Is that a function? If it
That's
returns-
not a function. So f of x equals plus or minus square root of x. And let's just go from like positive reals to positive reals. It's technically not a function. Because for a function, we need to associate exactly one element in the codomain to each element in the domain. And f of 9 is equal to 3, and it's also equal to negative 3. That's not a function.
So you added the positive reals. Was that fixed up? Because if
Oh, yeah, so let's go into all the reals, yeah.
so all reals wouldn't be a function.
Wouldn't be a function, but if you say you're going to the positive reals, then it's a function, yes. Was that your hand was up for? Okay, cool. So we're seeing where the domain and the codomain are pretty critical to the nature of a function, right? Sometimes it's not even a function, sometimes it's a function, sometimes it's not well defined. So I'm going to introduce some terminology. So let me try this with some pictures. There's a few different ways to do this, with pictures and with words and with equations. So let's suppose we have a function mapping from this set to that set. And I'm going to show you the entire domain. It's only 3 points, okay? And let's say that f maps each of those points to these 3 points, and let's suppose that's the entire codomain, okay? This is a very peculiar situation because every point in the codomain is being mapped to. In other words, the image and the codomain are exactly the same. So we call this surjectivity. And sometimes we use the word onto. We turn onto into an adjective. So we say f is surjective if it maps to every point in the codomain. So your example of x maps to x plus 1 on the natural numbers is not surjective, because nothing maps to 1, right? It would have to be 0, and that's not part of the domain. But if we map x to x plus 1 across all the integers, that is surjective. Every integer is equal to some other integer plus 1. So surjectivity is saying we map onto every piece of the codomain. All right, here's a different function. And this differs from the first function because in this case, it's not surjective, right? We're not mapping to this point. But there's another peculiar characteristic of this. We have 2 points mapping to the same point in the codomain. Okay, so we can talk about injectivity. And here we would say f is not injective. So an injective function means that different points map to different values. If 2 points map to the same value, it's not injective. If every point maps to a different value, it is injective. And we sometimes call this one-to-one. So these are our 2 main categories of functions: surjective versus non-surjective, injective versus non-injective. And let me give you some math to go with this, and then we'll look at some examples. So f a to b is surjective if and only if for all points b in the set B, there exists an A in the set A such that f of A equals B. So for every point in the codomain, there's some point in the domain that maps to it. F A to B is injective if and only if the following is true. For all A1, A2 contained in A, f of A1 equals f of A2 implies A1 equals A2. That's the same thing as the pictures, but this is a more formal way of saying it. All that this means is for any 2 points in the domain, if they have the same value, under f they must be the same point. So for example, f goes from z to z, f of x equals x squared. Is that surjective? What's the codomain? That's the image.
Oh, yes, sir.
What's the codomain? You just get that from the definition. That's the set of all integers. So is every integer the square of some integer? No. Again, there's no x that maps to 7. If there's at least one number over here that's not mapped to, then it's not surjective. How about injectivity? Is it possible that 2 different integers map to the same value under the map f of x equals x squared? Example? -2 and +2 both map to 4, so it's not injective. How about if we go from the reals to the reals? Is that surjective? Because -1, there's nothing that maps to -1. There's no real number that maps to -1. So that's still not surjective. Is it injective? Same problem with integers. -1 and +1 both map to 1. So it's not injective. If we went to complexes, we'd find that it was surjective, but no longer, still not injective. All right, so we'll play with some more of these properties tomorrow. We'll see different ways to look at them. And then Yeah, I'll do cardinality on Friday. We'll talk more about sequences and summations tomorrow. Only Friday for the weird stuff.